Hello, my name is Janis, and I'm a master's student at the University of Zurich and also part of the Geococcus team responsible for this paper. And this team is led by Simon Clematide and Martin Volk. In this talk, I will present our short paper called Ranking Georeferences for Efficient Crowdsourcing of Toponym Annotations in a Historical Corpus of Alpine Texts. So the goal of Geococcus is to link toponyms in the text and Berg corpus to geographical databases. Toponyms are mentions in the text of geographical entities like mountains, rivers, cities, and so on. The text and Berg corpus is a collection of yearbooks of the Swiss Alpine Club containing memories, reports from hikes, and so on. And these yearbooks are digitized and available with syntactic annotations. And like I said, we want to link all the toponyms in this corpus with geographical databases. These databases are GeoNames and SwissNames 3D. We use SwissNames 3D for all Swiss references or geographical entities, and GeoNames for all entities outside of Switzerland. So to give a quick example, let's look at the sentence shown on the slide. Oberarhorn, erste Ersteigung. Mönchjoch, erste Überschreitung. Alphubel und Alphubel-Pass, Fehlgletscher, Rümpfeshorn, sämtlich erste Besteigungen. Am Matterhorn am höchsten gestiegen, Dent de Rhin, erste Ersteigung. Here we have many mentions of mountains. All of these mentions are toponyms, and the goal is to link all of these mentions to a unique identifier in one of those databases which represents a specific mountain, or in other cases, it could be a lake or a city, and so on. We only consider a few entity types to make this entire project simpler. So we only consider cities, glaciers, lakes, mountains, mountain cabins, regions, rivers, and valleys. The basic idea of this project is to first collect annotations from the crowd, and for that we set up a website, and you can see a screenshot of that website on the right. With these annotations we can train models for named entity recognition and then use the output of that model for linking the entities to geographical databases. And we imagine this entire procedure as an upward spiral. So the idea is that more crowd annotations lead to better named entity recognition, which leads to better named entity linking, and better named entity linking leads to easier and faster crowd annotations. And to explain why this leads to easier and faster crowd annotations, let's quickly switch to the actual website. We are now on the Geococcus webpage, and in front of us we have one page of the text and Berg corpus. We see some tokens in yellow and some tokens in green. The yellow and green tokens have been predicted by the named entity recognition system as toponyms, and the green tokens have already been verified by users to really be toponyms. So let's click on one toponym and verify it. Here we see the toponym Lausanne has one entity candidate, and if we zoom out, we see it is the city of Lausanne, and this seems to be the correct entity candidate, the one that is actually referenced in the text, so we can just verify it by clicking the green button. Now we are on a different page, and we will look at Breithorn. We see one suggestion by the entity linking system displayed here, and we see that there are 5 more possible references for that toponym. Because we are not sure if this one is the correct one, let's look at the 5 other ones. So here we see the 5 other possible references or entity candidates. And again, if we are sure which one is meant, we can verify that candidate by clicking on the green button. As we saw in these examples, the annotation process is much faster if the correct entity is already the first suggestion. Now let's concentrate on entity linking, or in our case, ranking the correct entities on the first place. The first step for that is to search the database for entities with that given name. So looking at the example sentence below, the sentence that I read to you before, if we want to find entity candidates for Alphubel, we just search in the database for that string. And also the names are normalized to capture as much spelling variations as possible. Often, because many entities have the same name, such a search returns multiple entities or entity candidates for the same toponym. So to predict which of those candidate entities is the correct one, we use a ranking algorithm. Generally, this ranking is based on the hypothesis by Buscaldi that textual proximity indicates geographical proximity. So if some toponyms appear close in a text, they're also likely to be close geographically. To gather such proximity evidence, given a toponym, we use a context window around the toponym for evidence and no other features. So to understand it in more detail, let's look closer at how the algorithm works. And let's do this with this text example. We will focus on the word Alphubel and ranking the candidates of Alphubel for that text example. So here we see our target toponym Alphubel, and around that we see the other context toponyms, the toponyms that appear before and after Alphubel. Below the toponyms we see their candidates, and the correct candidate of our target toponym is marked green. Now, to use geographical proximity as evidence, we go through the context toponyms one by one. So we start with Oberaarhorn. And we build all possible pairs of candidates that involve one candidate from the context toponym Oberaarhorn and one candidate from the target toponym Alphubel. So basically, this is the Cartesian product of the two candidate sets. And then we compute the geographical distance of each of those pairs and determine the pair with the shortest distance. In this case, the first candidate of Oberaarhorn and the second candidate of Alphubel are closest, and thus the target candidate 2 is awarded a point. Next, let's look at Mönchjoch. Mönchjoch has only one candidate. So we compute the distance from this one candidate to the 3 target candidates. And again, give a point to the target candidate with the lowest distance to the context candidate. In this case, this is candidate 3. And we continue this with the next toponym, which is Alphubel Pass. And again, we give a point to the target candidate. This is part of the shortest distance pair. In this case, this is candidate 2. And finally, we do the same for the last context toponym, which results in a point for candidate 1. Now we got some points, and what do we do with those points? We use them for 2 scores, a window score and a yearbook score. The window score is exactly the result of that procedure that I just showed you. And the yearbook score is an aggregate of all the previous window scores in a yearbook. So for example, if an entity previously appeared 5 times as a candidate in a yearbook, the yearbook score is the sum of all the points the entity got in those 5 times as a candidate. Now, to compute the final score that we use for ranking, we simply map the yearbook score onto the interval of 0 to 1 and then multiply it with the window score. So this combination of scores is then used for this final ranking. And ranking then just means sorting the candidates by score in a descending manner. We also propose a re-ranking algorithm. The idea of re-ranking is that if a user verifies a candidate or marks a previously unrecognized toponym, new evidence is available and we want to use that new evidence. So the re-ranking algorithm takes new annotations made by users into account and adjusts the ranking on the fly. More specifically, if the user verifies an existing candidate or marks and links a toponym that was previously not recognized, then other candidates that are geographically closest to that verified candidate are rewarded 10 points instead of 1. As an example, let's look at the sentences on the right. We see toponyms marked in green. The goal is to rank the candidates of Breithorn marked by the red borders. So we want to look at the context, but our algorithm did not find entity candidates for all toponyms, only for the ones marked in gray. So let's look at the map and see what the results of the ranking algorithm is in such a situation. The blue marks are candidates for Breithorn. The number above the blue mark is their yearbook score, and the correct candidate is marked with a green circle, so it's this upper candidate. The other colors belong to candidates of context toponyms. The green lines indicate a minimal distance candidate pair, and the round purple mark denotes an entity that has been added and verified by a user after the ranking. So we see that the upper blue Breithorn candidate has a yearbook score of 1 and is in a closest distance pair with 2 context candidates because the purple entity is not yet recognized. And the lower blue Breithorn candidate has a yearbook score of 6 and is also involved in 2 closest distance pairs. So it is ranked first by the ranking algorithm, which is wrong. But when the user adds this new purple entity and we give the Breithorn candidate that is closest to that 10 points, because the purple entity is verified, then the upper candidate has a higher score than the lower one, and finally the correct candidate is ranked first. So after this long explanation, let's look at how good the ranking and re-ranking actually perform. To evaluate the algorithms, we annotated 20 pages of 2 yearbooks, 1864 and 1874. We chose the pages randomly, but they had to contain at least 4 toponyms with multiple candidates. And to evaluate the re-ranking, we additionally simulated a user that goes through the text from left to right and from top to bottom, and that marks missing toponyms and verifies candidates. We also systematically tested the approach with several window sizes and found that a window size of 4 works best. So the numbers that you see below in the table are for that window size. So let's look at the results table. We divided the results by yearbook, and as a baseline, we randomly sorted the candidates and then compared that with ranking and re-ranking. And to explain the rows, for each setting, we see how many correct candidates were placed on the first rank, on the second, and so on. So for 1864, we see that a random baseline leads to 34% of correct candidates on the first place. Then ranking places 90% on the first place, and re-ranking improves that to 96%. In the yearbook of 1874, we see some lower numbers, but still an improvement in each setting, so there is some variability between yearbooks. Now, in conclusion, we presented an iterative process for simple and fast crowd annotation, or more accurately, in this context, geocoding of the text and belt corpus. Since the annotation process is much faster if the correct candidate is already ranked first and suggested, we already want to present the user with as much correct first place rankings as possible. For that, we propose a ranking and a re-ranking algorithm. And the ranking algorithm is based on the textual proximity hypothesis, and the re-ranking algorithm additionally takes into account live user input. For the evaluation, we annotated 20 pages of 2 yearbooks, and we saw that this approach is quite effective. Finally, we will release the 2 × 20 annotated pages as soon as possible. So this is the end of the presentation. Thank you for your attention, and let's turn to the discussion now.